Before we move on, let's have a deeper understanding about this learning rate. So let's say we want to add this wi, that is defined as yi minus yi hat into xi. So how this comes, and let's say if sorry let's make a table. So if our yi, this is yi, this is yi hat, this will be our delta w. Okay, so whenever our y is 0 but we have predicted is 1, so we want to decrease it. So if we calculate here our delta w, we can see that eta is the learning rate. So we put 1 0 minus 1 here and take the xi, whatever is xi there, so it will always be negative. So we want to decrease, and whenever we have misclassified as 1 0, so if we put 1 minus 0 and eta into xi, so this will always be positive, so we will increase 1. And whenever we have predicted correct, let's say 1 1 1, so this will be 1 minus 1 0, so we don't want to change our w, so delta w will be 0, no change. This is increase, this is decrease. And whenever our input data is 0 and we predicted 0, we don't want to change our w, so delta w 0 minus 0 eta into x, that will always give 0, so no change. This is how we can interpret this as learning rate and why this formula is there. So let's come to this. Okay, before that I want to discuss about something that is OR gate. Okay, let's discuss it. So previously we saw that we have a positive input here, here and here, and a negative one here. So we said that our decision boundary should like this. So our w0 w1 multiplied with 0 plus w2 multiplied with 1, that will give greater than 0 for this one. If we say this is x1, if this is x2, so for this, let's say this say x1 x2, for point 0 1 we have w0 plus w2, that is greater than equals to 0. So we have for point 1 0, so we have w0 w1, that will be greater than equals to 0. For 1 1 we have w0, we will get 2, w1 w2 greater than equals to 0. For 0 0 we will have w0 less than 0. So if we solve all for this equation, this is solvable. So based on this w's, we can get this decision boundary that can perfectly divide the two type of outputs. Let's talk about the XOR gate now. In XOR gate, what we had, let's say this is our axis x2 x1, let's say we have 0 0 here, that is our negative, and 1 0 negative, we have positive input here and here, this 2 and this 2 negative. Okay, so we have the equation for 0 1 point, we have w0 plus w2, that is greater than equals to 1, that is equation number 1. For the point 1 comma 0, we have w0 plus w1, that is greater than equals to 0, that is equation number 2. For 0 0 point, this one, we have w0 less than 0, 3, and 1 1, we have w0 plus w1 plus w2 less than 0, equation number 4. For example, 1 and 2, we have w1 and w2 greater than w0, but for equation 4 we can see that if we give it as w1 w2 greater than equals to w0, so we cannot satisfy this equation 4. Based on first equation 1 and 2, we get this, and equation 4 does not comply with equation 1 and 2. So a single perceptron, we can say that a single perceptron cannot classify Zorget. The single perceptron here also cannot classify Zorget, and we have seen in MP Neuron 2 a single perceptron couldn't do that. So what is the solution to get rid of this? So we take a network of perceptron. So here we can say that we have input layer is, say this is x1, this is x2, our input. So we add a hidden layer in between this input layer and output layer. Previously from input we are calculating something and we are getting output. Here we will not directly go to output, we will have a hidden layer. Hidden layer is nothing but some neurons lies in between input and output. So we first calculate this, then from this outputs, let's say h1, h2, h3, h4, from this output we will get this. We take these outputs at input for this layer and we will get the result, desired result. This is called a neural network. This is an interconnected mesh network. So where we will have input layer, we can have multiple hidden layers. If the one single layer is very so many neurons in one single layer, this is called deep neural network. And we have output layer, so we can have multiple hidden layers. We can have one hidden layer here also, one hidden layer here also. So we can have 3 hidden layers, or we can have one hidden layers with multiple neurons in it. So how this architecture will help us, let's see. Let's try to solve this Zorget now. So what was the problem? The problem was that the two equations contradicted with each other. So we had positive here, we had negative here, positive here and here. So we had 4 equations, but 4 equations contradicted with each other. So here the architecture will follow is that we have x1, x2 two inputs, and we will get 4 neurons at the first layer. We will connect everything with this as you have seen in the photo, and we will have this 5th layer, so that will take all this output from this previous layer and give the final output.